So this is something else. I think Morgan posted this in the Slack, and this is a paper from the. There's this. It's on scientific replicability. The lead author on this paper is Brian Nosek, and so this article is titled "Investigating the Replicability of the Social and Behavioral Sciences." It's very ambitious because there's a lot of social and behavioral science out there. But basically, they're doing a meta analysis on the field, and they have this interest in replication and replicability. And so, when we say replicability, what are we referring to? So, basically, in science, one of the things that we try to do when we do experiments is we would like to, first of all, have a controlled experiment where we have a hypothesis and then we set our experiment up so that we can test the hypothesis without too many confounds. So the idea being is that when we have a hypothesis about, like, say, if I move my mouse across the screen, I'm doing something with my hand, there's motor control involved. And if I perturb that motor control in different ways, for example, if I have a distractor light in the periphery of my visual system, it will slow down my ability to move the cursor across the screen because I'm distracted visually by that thing, and it disrupts my sensory motor integration, and so it's my movement is slower. And then you could have a control where people aren't distracted by the light, experimental condition where people are distracted by the light, and then have different levels of distraction, so that one is obviously going to have an effect, and maybe one has a minimal effect. And you predict all this in advance. You design the experiment so that you can test the relationship in a very isolated way, and you try to eliminate confounds, which are things that will maybe could be other potential causal mechanisms or effects, and you try to minimize the interactions of different variables. So you just want to have the two variables, or that you're testing. So you have a very clean. If you have a very clean experimental design, first of all, your effect will pop out, and you'll be able to see the effect. You can use statistical testing to confirm that effect. And then, of course, you have an effect size, which depends on the number of people who are in your experiment. And then, of course, you have this idea of replication. So if I design a good experiment and I have this result, I can, do all sorts of different statistical tests. I can even do causal modeling and say this is, the effect and it's real. But another way to know that it's real is to replicate that result. To do like 10 experiments and have them all basically point in the same direction. Or have 10 different groups do the same experiment. And why do you want to use different groups? Because different groups will implement this slightly differently. They might use different variations on the light. They might use different variations on the cursor speed and so forth. So you have, if the effect holds up across these different variations, then you know that the result is robust. So that's the idea behind replication. We'd like to see replication also because if we're trying to apply our findings to, applications, like if we want to build this into a computing paradigm, like a user interface, we want this to be something that is robust. So if we say, we want to build this result into a GUI, we want to make sure that this isn't just some result that's not very well supported and is maybe the case only about a quarter of the time, because that would be, it would result in a bad product. So replication has a lot of uses in, in the behavioral sciences, but also in other areas where we do experiments. And the thinking is, of course, is that physical systems or physics, you can replicate things very easily, or maybe in chemistry, because those are physical systems, and we have a very high degree of characterization of those systems. And quite frankly, they're not as complex as social systems, or so the thinking goes. So a lot of people who do biological experiments and social science experiments will say that I can use experimental techniques, but they're not going to be as replicable as those in physics and chemistry, simply because it's harder for me to isolate the different variables involved and not get interactions and not get confounds. Because, in biology and in social science, you have a lot of, sometimes you have uncharacterized variables, sometimes you have a lot of things that are interacting, and it's just really hard to isolate those things, and then also make that experiment useful for understanding the system as a whole. So we can do experiments in biology and social science that are very contrived, but they have very low, what we call ecological validity, or the ability to transfer those results to um, to reality. What does that mean in reality? What does that mean in like a real social setting, or a real psychological setting, or a real biological setting? And a lot of times our experiments are just that. They're sort of artifacts of that don't have a lot of application outside of their own domain. So this is kind of where we sit with this. So the idea is that replication, we kind of assume that replication is the gold standard. In the social sciences, because of the factors that I mentioned, it's hard to get experiments to replicate. So this has led to something that they call the replication crisis, which is that you can do all these experiments and get these results, and if you go back to the literature to try to reproduce a lot of experiments, sometimes a lot of famous experiments, you can't replicate them. And this is a thing that is sort of the basis for this science reform movement that you might see. Brian Nosek, of course, is very interested in this. There are other people as well, which is that we need to improve science by finding better ways to do science, finding better ways to standardize science, because we want to have more replicable social science, more replicable biological science. Basically, where we can't replicate something, we should try to rethink how we do experiments, how we do data analysis, so that we can make things more replicable. And of course, then there's this other school that says, well, we really can't do that. We just have to go with what we have. And, that's just kind of our heuristic. And that's the best we can do. And I wouldn't worry about it too much. So, there it is a debate. So when they present this stuff, it's interesting, and it's, I think, useful for understanding where we stand in the science, in the social and biological sciences. But it's also very much, um, you know, maybe we can't expect to use experimental methods and really expect to have highly replicable results. Maybe the best we can do is like quasi experimental methods that give us indicators of what things are, effects in social science. If we have an intervention, for example, there's certain effects that we should expect, and it's not going to be very easy to replicate those across different labs or different contexts. So that's kind of where we are with this. So let's go over the abstract of this and then a little bit into the paper. So as meta science, what they're doing is they're taking a bunch of different results from different papers that have been published, and they're reevaluating those, and they want to understand kind of as a whole where we sit, how replicable are claims that get published. And sometimes they're very famous results, and sometimes we base a lot of our theories on them, or a lot of popular sort of science, popular ideas about how the brain works, for example, on them. So, there have been a lot of examples in psychology where you've had famous results that have everyone has kind of hung their hat on, and then they turned out not to be replicable. And so this is a little bit of a ding on some of the cognitive science techniques that have come out of the cognitive revolution. So, in any case, let's get into the abstract. Pursuing replicability or independent evidence for previous claims. So you do an experiment and you publish your results and you observe the effects there. And then some other group tries to do the experiment again, and they either get an effect, and maybe it's of a different size because sometimes you don't get the same number of subjects. Sometimes those subjects exhibit variability. Sometimes your environment is a little bit variable. And so you can't expect the results to always be exactly the same, but you should get them in the same direction. If they get a positive result, you should also get a positive result. And you should be able to do this in any kind of setting. So, like, again, if I want to confirm some finding, I just simply run the experiment for myself and I get that result. And as we know, we can do that. Actually, we have a version of this in computer science where if you run things in a container, the whole concept of that is that I will write a program, execute it on my machine, and then if you execute the program on your machine, you might get a different result because your machine is different parameters, has a different processor, whatever. But if I put it in a container, I can always run the program exactly the same way and get the same results. So there is a version of this in computer science. Unfortunately, we can't containerize social and behavioral science experiments or biological experiments. So that's something to keep in mind. So this allows us to have generalizability, which in machine learning we worry about with training models. But in a lot of these experiments, we want to design experiments so that the results are generalizable to any kind of replication and eventually even to application domains. So here we attempted replications of 274 claims of positive results from 164 quantitative papers published from 2009 to 2018 in 54 journals in the social and behavioral sciences. So a wide range of different findings published recently. So this is, 2009 to 2018 is well within this sort of science reform era. So this is like, if you go back to like the 80s and 90s or even the 70s, you can go back there and find a lot of experiments where people were totally not thinking about this. They were very not thinking about replication too much. Sometimes they were, but a lot of times they weren't. And you might say, I'll take some experiments that were published back then and reinvestigate them, and lo and behold, they don't replicate the way I expect. Well, that's maybe unfortunate, but it's not something that where people are actively engaged in this conversation. But from 2009 to 2018, this conversation was going on. So, you might say, well, people were, just trying to run their experiments and live their lives. But the idea being is that, people are aware of this problem and it still persists. So, and I will say that the Nosek group and some of these other groups, they have a specific sort of agenda for this. It's not like they're picking on people, but they do have this idea that, science needs to be done a certain way. So this is, and they want to sort of advance their own research in science reform. So there is that aspect of it. So, I'm not saying that like people are just being intentionally dense about science reform. It's just that that's where we are in this debate. So they had a pretty good sample of different studies to look at. Replications were high powered on average to detect the original effect size, with a median of 99.6%, used original materials when relevant and available, and were peer-reviewed in advance through a standardized internal protocol. Replication showed statistically significant results in the original pattern for 154 of 274 claims, which is around 55.1% of studies surveyed. So this is, maybe not great. It's over half, but it's only about a little over half. So this means that, if you have experiments that you take out of literature at random, only a little bit more than half of them replicate. And that's, again, this is using sort of the, as close as we can get to the original experimental design. So, that is kind of disappointing maybe. And for 80.8% of 164 papers, which I don't know how they get to 80.8 of a paper, 0.8 of a paper, but I think this is just a weighting scheme, weighted from replicating multiple claims per paper. So this is where, they make more than one claim from, or maybe more than one experiment in a paper, and you're kind of looking at this in its totality. So we're really kind of when we do that, we actually get a little bit below 50%. So actually, if you think about this as an at-chance endeavor, like if we ran 1,000 experiments and we got 50% of them that replicated, that's kind of at chance. That's not, but that's one way to think about it. There are probably reasons why this exists. I don't think people are doing a poor job of experimental design, but they never really kind of get into that in these papers. They always kind of just show that there's this lack of replication. And, the implication is always that there's a problem in science. I think probably a lot of this is going to be like psychology or something psychology adjacent. But maybe it's just, again, the complexity and the nature of social and behavioral sciences, that it's very complex and it's hard to kind of isolate phenomena in a way that sort of like physics. Okay, so we observe modest variation in replication rates across disciplines, and depending on the discipline, it ranged from 42.5% to 63.1%. So maybe some disciplines it's really hard to replicate. In others, it's maybe easier to replicate, but really, you don't get anywhere near 100%, and you don't necessarily get anything near 0% either. So, and then some estimates, though, had a high uncertainty. So, again, we're making an estimate about this based on this sample of things, and it's, I guess, a representative sample, but, we're hovering around 50%, kind of around that area. The median Pearson's R effect size was 0.25 for original studies and 0.10 for replication studies, which is, of course, there are replications in the literature, and of course we expect the replications, maybe from what we're saying here, to not be as robust as the original studies. So again, we're finding this, we're kind of confirming this idea that the original studies are not great in terms of replication, but the replications aren't great either for obvious reasons. 13 methods for evaluating replication success provided estimates ranging from 28.6% to 74.8%, which is a median of 49.3%. Some decline in effect size and significance is expected based on power to detect original effects and regression to the mean, because we replicated only positive results. So you might be able to replicate a negative result, but that's not that hard to do. I mean, you do a poor job of setting up the experiment, and of course, I got a negative result too. You don't even have to run the experiment to get a negative result, I guess, technically. But so having the positive result, that's sort of the thing that requires you to have good experimental design. A negative result doesn't necessarily require that. We observe that challenges for replicability extend across social and behavioral sciences, illustrating the importance of identifying conditions that promote or inhibit replicability. And again, this is assuming that you can do this in the same way that we kind of have a mental model for. So, again, why do we care about replication? Well, one of the aims of science is to discover regularities, statistical regularities, and sort of structural regularities. And one way to do that is to say, if I run an experiment and I get a positive result, if I rerun that experiment, I should get a similar result, and I should always get that result if this is a phenomena that's true or that's real. If it's not real, I might get a positive result once and then a negative result again, and maybe I keep getting a negative result, and then maybe I get another positive result. And this is not trivial, because basically when we do when we assess statistical significance, that's essentially what we're doing. If we had, say, 20 experiments, we should expect, if we have, say, like a 95% percentile criterion, that we should expect 19 of those experiments to be positive, to be successful, to show the effect, and one experiment that does not. So depending on our significance criterion, we should expect out of those 20 experiments a certain proportion of those to replicate. I mean, that's essentially what we're saying when we do like statistical significance. We should say for 20 observations, vast majority of them should be in this direction. And there may be some in the other direction. But the reason why we have the significance criterion is because we want to say that, like, for the most part, this is true. There are always exceptions. So, people have talked about statistical significance before. There's this whole side debate about, like, the value of looking at statistical significance, and how people do things like p-hacking to try to make something statistically significant that otherwise wouldn't be. So there are all sorts of problems there as well. But the idea is that we want to discover these regularities. So we want to be able to replicate our results so that every time we do an investigation, we can get similar results. And it should be reliable. And especially if we have something that is an application, we want to make sure that it's a repeatable result. And so then, they talk about this replication crisis and how a lot of published work will claim, well, it doesn't claim replication. It's just that they're published as positive results, and a lot of times people don't question that, and they kind of run with the result. And so this is a problem that we have, especially in things like cancer biology, where the stakes are pretty high, right? We need to be, if we have a clinical trial there, it's actually pretty important that we can replicate it. And a lot of times we can't, and I have thoughts about that, where, it's like we're dealing with very complex systems, and in fact, with cancer, it's very, it's highly variable in terms of how you observe these things. And so there are a lot of things there that kind of work against really good experimental results. But anyways, so they get into this. Popular explanations for the low observed replication success rates include underreporting of negative or inconclusive evidence for claims, high sampling error from small samples, and measurement error due to unreliable measures, coupled with a statistical threshold that serves as a publication filter. So there's this idea that, like, sometimes when we, to get things published, we need to achieve a certain statistical threshold of a p-value. And so if we can't get to that, sometimes people will try to get to that using, less than rigorous methods to get there. And this is something that is maybe a problem, because a lot of publications won't publish negative results. And if they don't publish negative results, of course, then people don't get published. And there's a whole incentive structure that is immobile in this case. So This is where you have to publish positive results. You can't publish negative results. So there's pressure to get positive results, even if it means sacrificing replicability or, just simply doing something more nefarious, like excluding samples that don't meet the statistical threshold. So that's kind of one of the points there. Low rigor and quality control in research, design, and measurement. So if your experimental design is poor or you don't, control for all of your confounds, and questionable research practices that inflate the likelihood of obtaining positive outcomes. These factors are compounded by a research culture that rewards novel and interesting findings and discourages error correction. Again, these are just these incentives that are misaligned with the ideals that we would like. Replication failures are not necessarily due to the original findings having low credibility. Low replication rates can also be due to false negatives, poorly designed replications, selecting only positive results for replication, and differences between original and replication studies that are initially perceived as unimportant. More broadly, there are conceptual challenges in deciding what a replication of a previous finding is and how to assess whether replication attempts succeeded. So we sometimes, even just using like meta-science, maybe meta-science, the problem is meta-science. Maybe the problem isn't in the literature. But that's something that is a little bit more, that's maybe requires a meta science. But I think really, this is just kind of an interesting kind of a way to think about our results that we read. Whenever we read a result, is this something that is, can we trust this result as replicable, or is this a one-off result that is interesting, but it's not going to, we really have to think through this problem some more. Interestingly, I know there are a lot of people who critique benchmarking in computer science. So benchmarking kind of suffer from the similar kind of problems we see here, where you have two programs and you benchmark their performance, and a lot of times people are trying to optimize performance down to like a couple decimal places. And how effective is that really? I mean, you can game those kind of statistics pretty easily. And so, sometimes people will, want to show that their model is better performing than another model. So there's a temptation there to sort of game the system for your model. There are a lot of challenges in benchmarking as well, and I haven't gone and found a good critique of this, but maybe I'll do that next time. So they go through this study here. This is table 1, papers and claims selected by replication attempts by discipline. So they cover business, economics, education, political science, psychology, sociology, and then the total at the end. So we have claims selected and replications attempted. So they've selected a number of papers with claims, and then they have that number there. So they're sampling, I think in psychology they have 950, in education they have 445, and there's a range of number between that. Papers eligible for replication means, which papers can we actually replicate the claims with. So that's a subset of those. Papers with multiple claims, they're a smaller number with that have multiple claims in them or testing multiple hypotheses. And then papers with a single claim, which is the balance. So the papers eligible for replication, those are the ones that will be the replications that they attempt. So not all of the claims can be replicated, or they don't think they can, or they won't. So they do a subset of these. And I don't know what the criterion for deciding that was, but that's, that is up to the team that did the paper. So they had papers with replication started, papers with replication attempts completed, total replication attempts of claims, so that's a smaller subset still, and then unique claims of replication attempts. So this is how they kind of divided this out. They took a bunch of papers from different fields, they examined their claims, they then took each claim, actually they took each paper, and they then looked at the claims and they figured out which ones they could replicate, and then they did the replications, and they ended up with a much smaller subset of replication attempts completed. So this is, again, where we have a bunch of things in the literature and we kind of winnow it down to things that are sort of low-hanging fruit or easy to actually do in an environment. So we're getting like the kind of the simplest experiments, or the most, maybe the most important experiments. And so there is this selection bias here to be aware of. That is, we're not testing every claim, we're testing a subset of claims. And yeah, so I mean, there might be something to say about that, where you're kind of testing the things maybe that are the least replicable, or maybe they're the most replicable. It's not really clear. So that's basically what we have here. So you're making, and if you look at the numbers, actually, I don't think there's a huge sort of bias towards any one discipline. I think, I think psychology, it's a little bit more replicable, or maybe you had more attempts in psychology than in other areas. So you had papers with replication attempts completed, 58 in psychology. You had started with 950 papers with claims. In education, you have 13 versus 58. And for education, you had 445 papers. So there's a little bias, I think, towards psychology. And because the team is, Brian Nosek's a psychologist, and the team probably knows psychology better. This is probably why you have this bias. So, again, this is not, like, the experiments are behavioral experiments, so they're not going to be wildly different from the typical psychology experiment. So that's kind of why, just something to be aware of here. Okay. So for table 1, representativeness across disciplines was maintained during identification and extraction of claims because we use random sampling strategies. Most of the change in representativeness occurred owing to the non-random process of selecting and starting a replication study. So education and political science decreased in relative proportion of the sample, and psychology increased. Okay, that's, again, what I just talked about. Compared with the original sample of papers, the proportion of completed attempts of unique claims was within 3.5% for economics, education, political science, and sociology, and more notable variation was observed for business and psychology. Representativeness of replication attempts was relatively steady by year compared with the sample papers. We selected papers and attempted replications in 2 phases, with 139 of the completed replications occurring from papers selected during the first phase and 25 from papers selected during the second phase. Replication success rates were similar between the first and the second phase. Okay, this then is figure 1, which is the replication success rates across 13 binary assessments for papers. So what is this? This is where we have binary success measures, and for different things, and then proportion successfully replicated according to measure percent. So these are the different sort of ways in which, I guess, things are assessed. So you have this measure of success. You have meta-analysis at the top, which is where, I guess there are these different types of mechanisms or different types of measures that they're binning things into when they're looking at how replicable those measures are. So meta-analysis comes out on top, and then you get small telescopes, Bayesian meta-analysis, replication effect and prediction interval, subjective interpretation, replication Bayes factor, then skeptical p-value is down the list, sum of p-values is down the list, correspondence test is right with the p-values, Bayes factor is down below, and then the original effect and replication confidence intervals. So the confidence intervals are at the bottom along with Bayes factor. So I'm not quite familiar with these success measurements, but it's interesting that sometimes Bayes and Bayesian stuff comes out on top or near the top, and Bayes factor comes out low, confidence interval comes out low, and then correspondence tests, which are usually pretty weak statistical relationships, come out with p-value measurements. So I'm not an expert at in these different measurement techniques, but it's kind of interesting how those are distributed. Okay, so they talk about this a little bit more. This problem highlights a challenging problem, or this project highlights a challenging problem. Replication success metrics can be applied only to methods that meet their assumptions. So again, sometimes people use metrics where the assumptions aren't met by the data. So this is something that, again, is maybe a problem in replication, is that people use different metrics or they use metrics incorrectly, and that can always be because metrics always have assumptions built in. So this is a problem, which you would think would be corrected in peer review, but oftentimes is not. People will give justifications for using a metric that maybe they shouldn't be doing. Okay. And so in figure 1, we present 13 replication success metrics. Some are necessarily binary assessments of replication success or failure, and others are simplified to provide a binary assessment for comparison. Okay, across metrics, replication success rates range from 28.6% to 74.8%, with a median of 49.3%. So that number again, 49.3%. The observed variation highlights the impact of different assumptions underlying each approach. For example, the highest estimate of 74.8% for the meta-analytic combination of the original and replication evidence provides strong evidence of success because it includes original studies that provided evidence of success, and these tests are not independent of the original evidence. Variation in the observed replication rates are affected by both the assumptions of the binary assessment and the subsample for which the metric could be used. Figure 2 presents correlations between each pair of binary assessments for replication outcomes, which both methods can be applied. So that's this figure here. And then this is where we have these different metrics kind of compared to one another. And then we have this distribution of all 144 correlations. So this is just kind of thinking about these correlations between different metrics and how these are distributed. So, let's see. Correlation values are to the right of the diagonal over here. And so, what does he say about that? Figure 2 presents correlations. Spearman correlations were positive and relatively high, with some exceptions. For example, analysts almost always interpreted success on the basis of statistical significance, as reflected by a correlation of 0.98, whereas measures that use confidence or prediction intervals show relatively strong correlations with each other. And so this is where, again, we have this different types of measurements having, sometimes they lead to high replication, sometimes low replication, sometimes specific types of measures are interchangeable. But also, if you're using other types of measurements, they aren't as consistent. So sometimes, you'll have a replication where you use, say, like a confidence interval, and another one where you use a Bayesian method, and you're going to have a different result. Is that due to the experimental design? Maybe not. Should we do that kind of test? Perhaps, because sometimes it can tell us about how robust a result is. And so, again, this discrepancy in different methods, using different methods for the different studies, is partly because because they treated replication outcomes both smaller and larger than the original outcomes as failures to replicate. So there is this aspect of statistical testing and their effect on replication. Okay, so the discussion here is about half the findings from a sample of social and behavioral science papers published between 2009 and 2018 replicated successfully with variation and success estimates across 13 binary assessments and effect size comparisons. Variation in replicability across disciplines was modest, with replication rates between 42.5 and 49% for fields that had more than 20 replications. These findings are consistent with the cumulative evidence across systematic replications, and they illustrate that there is substantial uncertainty in estimating replicability. Okay, so there's some conceptual, methodological, and inferential challenges to assessing replicability. Conceptually, it can be challenging to attempt a replication. Strictly speaking, there is no such thing as an exact replication. Of course, we want to get it as close as possible, but we can't always replicate the exact conditions under which the data were collected. There are always differences in units, treatments, observations, and settings. Researchers must make decisions about how to conduct a good faith replication on an original claim. So, for example, should a present day replication of a 2009 US study of political behavior that used President Obama as a stimulus use Obama again, or the current US president, or use the leader of the participant's nation? So, if you study people in another country, are they going to respond the same way as the people within the country where the leader is from? So, this again is like something that you do a study and it's interesting for what you want to find, but then it might be very highly contextual and replicating that study may not hold. So, but this is interesting because a lot of times we will take a study like this and extrapolate out the effect. So you might say something of, does this result say something about the context of the United States and President Obama, or does it say something about more generally, electorates around the world and their respective leaders? It may be very constrained to the U.S. context. It may not. So this is a problem that you have with studies when they're set up and studies when they're replicated. Another thing we have to worry about is as to whether or not the theoretical commitments are correct. So sometimes we have a theory, and this is something that the theoretical commitment might be wrong, where you have sort of you interpret your result in a certain theory, and of course it's the wrong theory to interpret it with. So then methodologically it can be challenging to determine how to measure replication success. So again, we have these measures, these metrics that they use, but again, you can't use a single metric universally, and a lot of times it depends on the measurements that the original studies used, and there are a lot of problems there. And then inferentially, it can be challenging to determine whether original and replication studies produce the same outcomes. Each of the replication assessment criteria has strengths and weaknesses and may be based on different assumptions. For example, metrics combine original replication evidence that are not independent tests and have relatively low sampling error. These tended to suggest the highest success rates. So again, tests that are not these tended to suggest the highest success rates. They might be useful only when it is safe to assume no selection or publication bias, and the emphasis is on cumulative evidence. So again, different types of studies may be more amenable to replication. And different types of ways to study replication are only useful in certain contexts. So you don't want to assume that studies were free of selection or publication bias when they were, and you don't want to select a study that has selection or publication bias. Okay, in summary, the question, did it replicate, can be difficult to answer. Fortunately, the answer for any given study does not matter much in the long run. Research is conducted on a study by study basis. Replicability is established via a cumulative body of evidence. So sometimes when we have a hypothesis or a theory, it's not so much that it's whether it's replicable or not, it's that if there are 100 studies in a certain area and they all yield different results, we can kind of figure out what the right answer is by looking at the accumulation of results. In other words, if a study is published and it turns out that it's not true, that the result is maybe a one off, it doesn't really hold true theoretically, then we should be able to detect that by looking at 100 different studies and looking at the direction in which they point. And if a study is pointing in the other direction, then maybe we just are skeptical of it and we don't need to worry about replication because we can kind of figure out the correct direction of what these findings suggest.